Ballast is the stone used to form the track bed on which the sleepers sit, with more ballast then packed between and around the sleepers. By any measure, volume or mass, it is the largest of railway components and is a critical part of the overall track system. Ballast is normally basalt or granite rocks. In the past, a number of different ballast types have been tried, such as ash, gravel and limestone. Although they each had their positives, their drawbacks made them unsuitable. Basalt and granite each exhibit the key attributes required of good ballast material. The stones are angular with defined edges. This allows individual stone to interlock well with each other. This gives strength and stability to the overall ballasted area, helping to resist the forces it will be subjected to. Ballast stone should also have good resistance to weathering. After all, it will be exposed to the elements and all weathers. The stone should maintain its angularity and not become rounded, like a pebble. It should also be resistant to chemical degradation, from oils and other things that may be deposited by passing trains. It should also have a good hardness value and the impact resistance to withstand the loading and unloading cycle of a passing train. Resistance to attrition and abrasion will also prolong its life, as well as preventing the creation of fines, which can lead to problems within the track bed. Fines or dust from the ballast can clog it up, stopping water draining through. Lastly, it should not absorb water. Water or track beds do not mix well, and the presence of water can lead to fundamental issues within the track bed, such as wet beds and track geometry problems. This brings us onto the functions of ballast, once it is put down on the railway. 1. It distributes the load of the passing trains from the rails and sleepers above it into the formation and ground below it. 2. It allows water to drain through it into either the underlying ground or the track drainage, if present. 3. It prevents the track moving laterally through ballast shoulders at the outside edges of the sleepers. On curbs, the lateral forces of passing trains push outwardly on the rails, and in hot weather, as the rails expand, they can also try to push the track outwards. 4. Ballast prevents longitudinal movement of the track. Full beds between sleepers restrains any movement from the sleepers. The ballast provides resistance to both longitudinal and lateral forces by pressure on the sleeper ends, and then friction on both the sides and bottom of the sleepers. With wooden sleepers, the ballast will create indentation in the sleeper, increasing the friction. 5. Lastly, an important but often overlooked function of the ballast is to allow repairs or redesign of the vertical and horizontal design of the track. As the track structure ages, it will develop faults that can lead to dips or other geometry issues. The free nature of ballasted track, compared to fixed track systems such as slab track, means that the track can be moved back into position by lifting it and packing additional ballast underneath or slewing it back into the correct position. This can be done manually or mechanically, with engineering trains such as tampers or stone blowers. Ballast is an integral component of the track system, and when well maintained, it provides important functions in supporting and restraining the track while allowing water to drain away quickly. Although other systems, such as slab track, exist, the maintainability and effectiveness of ballast track show why it is the most used railway construction.